Hello everyone. Um, this is the map 6 and the second part of data analysis. Uh, Here, this is again like always, this is our the website the detailed website of the course. We click on the course content and there's a section here, Computer Lab 6 Data Analysis, Part 2. So here is the PDF file and this is the source file. I encourage you to download the RMP file, and once we download it, we drag it to desktop and we don't need any more the detail. So we create a directory here, for example lab 6, and then we put it into drag into the directory. Now we want to we click here and we open this RMD file with RStudio. By this technique, like always, we set this folder as our directory. So here, if you have, this is the source file of the section lab 6, and if you can compile it or read it, and then you have the access to everything about it, all the sections, but we want to talk to each other one by one, these commands and these code, these are commands. So the first section that we want to learn how to calculate, if we have a data set, how we can calculate the mean and the standard deviation of a data set. So the data set that we selected is the data set car, which is a built-in command. So if we run this part, so you'll see that again we highlight it and we select run selected run, and then you will see that if I just click here car, so it gives me entire of the data set. So our data set has two variables. The first one is speed and the second one is the stopping distance of the car. And we want to work with this data set. First of all, because it's a data set and I want these two variables are local variables stored in the data set cars. So as we learned in the first part of the data analysis, we use the command attach to to determine for R that this is the data set and we want to have access to the data set. The variable inside we don't not to use in order not to use always the dollar sign. So now by using the attach, so now our studio has access to the variable inside the card. So now we can easily calculate the mean and the standard deviation of the variables. For example, we want to focus on the first variable, speed, and we want to find the mean and standard deviation of the data set, the first one. So if I just type speed here, so you will see that we have the data set. Now we can calculate the mean of the data set, in other words, the average of the data set. So if you just select the mean, so you can simply by the command mean, it simply gives us the average of the data set. And then if I want to calculate, or you can calculate by manually, you know that in order to calculate the mean becomes the sum of the data set divided by total number of observations. So the length of the data set gives us the number of observations, and the sum, of course, the sum of the observations. So if I run this line, so I say that calculate this sum divided by n and put it in the variable x bar. I created, for example, in an x bar, and then show me x bar. And you see that the value of x bar is exactly the same as the mean of the speed. But I encourage you to always use this command simply and calculate the built-in command mean. If you want to learn the variance of the variable in the course, we see that it is very time consuming to calculate the variance. But easily by command var, var, you can calculate very simply the variance of any data set you have. So, right, for example, the data set of the speed, we can easily calculate the variance is 27.95. And we know that the standard deviation is s square root of the variance, but we have a separate command, sd, in other words, standard deviation of the data set. The calculate the standard deviation of this bit is 5.2. And then we can detach the command, the R, and now we don't have any more access to the speed and other variables. So we see, but if we have one, so we can say that if we want to calculate again, mean, cars, dollar sign, now you can select speed and this can calculate for you. Anyway, the next thing is that we want to learn how to calculate five number summaries and how to create a box plot for the data set. So in order to five number summary, again we want to calculate the five number summary of the cars. So here the first 6 rows of the car, and then I attach the data set car because I don't want to work with the dollar sign always. So in order to calculate the summary, five number summary of the data set, it's very easy. You just need to type the command summary of the data set variable. It gives you the five number summary of the data set. The first one, you see that it means first quartile, median, mean, third quartile, and the max. Of course, it is more than five number summary because it also gives you the mean. But in the course, we learned that the five number summary are the minimum, first quartile, median, third quartile, or maximum. But by typing summary, it gives you entire of these 6 numbers. Or you can use manual separately by command median to calculate the median of the data set, and you'll see that the median is again 550. The only thing I need to highlight is that the algorithm that the R uses to find the median in the first quartile and the third quartile is a little different from what we learned in the course. So that's why sometimes if you manually calculate the first quartile and the third quartile, sometimes your value is slightly different from the value that I suggest because it uses a different algorithm to calculate those values. Anyway, so once we have a five number summary, so we can simply calculate the box plot of the data set. And the box plot we can create by the command box plot, the same name. So if you run it, so it gives you the box plot, the vertical box plot. You know that this line, the first line, shows the location of the median, which is 15, and the upper bound gives you the third quartile. This one gives you the first quartile. This line is the maximum, and this one is the minimum. But we have some options for box plot. For example, if I want to have my box plot to be horizontal, so you need to determine the option horizontal equals to 2, because by default the horizontal is false. If you want to change the color of the color of your box plot, you can use the option color. And for example, I want to have a box plot orange, and then I want to have a capture for the box plot. So if I run this one, you'll see that it creates for me a horizontal box plot, and this is the title of the data set, exactly as I determined, and then the orange is the color of the box. So that was about the second section of the data set. Now we want to see that how we can find a steam plot of the data set. Very simple, because we have already data set car. So head of the car. Now this time I don't use it. I just want to change it, and instead of attaching the attach, I want to work directly with the dollar sign. So I want to use the steam plot of the first variable in the car. So I just use the command steam, so it gives us the steam plot of the data set, or you can use that reverse, the data set of the reverse. We worked last session. The steam plot of the reverse, you can calculate them, and you see that from the steam plot, there's a huge data set here, and then we have the long tail, and it is clearly this is the skewness. It's a right skew data set. If you look at the box plot of the data set again, you'll see that look at this line tells us the first quartile and the median, and you see that 25% of observations are in the very tiny area, and the 25% of them, the right 25% is in this area. And clearly you see that how large this side, how larger this area is, and that's what it tells us that there is a skewness in the data set for the symmetry of the, if it wanted to be symmetry, it should be the same. The left side and the right side of the box should be the same. And then of course we have our higher data set. The next piece of the code is about scatter plot, correlation, and regression. So in this case, I will again we want to work with the data set of the car. We have two variables, and we want to work with the speed as explanatory variable, and the distance, the time that the distance takes the car to a stop. So it's as a response variable. So we attach the data set car, and then we have, in order to calculate the correlation between these two variables, we can use the command car, C-O-R, correlation, and then it gives us the correlation between these two variables. Inside the code, it was very, very time consuming to calculate the correlation between the two variables. But here we can very simply, in less than a second, we can calculate the correlation of the data set of any size. The next thing is that we want to learn how we can find this, how we can make a scatter plot of the data set. So we can find a scatter plot of these two variables, the speed and distance. I want to have a speed because the speed is the explanatory variable. I use the command plot. So I recall the first variable. The first variable should be, it goes to your x-axis, and then your second data set, your second variable is plotted on the y-scale. And of course, I want to have the label for my x, provide some information or label for my x-axis, which should be car speed, and the label for y-scale is the stopping distance. So if I run this command, you'll see that it gives us a scatter plot of your data set. Here the car speed, and this one is the distance, and you'll see that there is a strong positive correlation between them because we calculated the correlation is positive. That's why you see that they are positively correlated. As long as the speed increases, it takes more, we need more distance to stop. The car requires more distance to go further and further to stop. And now it's time to see that how I can fit, how can I describe this one by regression line. So in order to find a regression line, you can use the command ln. It's the abbreviation of the linear model, ln. Now for the linear model, you need to determine the first argument, you need to determine your response variable, distance, and then we type tilde here. We have to use the tilde to show that we have the model formula, and then we write the explanatory variable. So it means that I'm interested in the regression of my response variable distance and my explanatory variable this speed. And then I say that calculate this regression and save it into the argument my regression. So if I run it, so the calculator, I want to see that the output of the data set, the regression line. Now it says that if I recall it, it says that your model, the formula is the distance on speed, and then the coefficients A in our intercept of the regression is negative 17.57, and the slope of this regression is 3.93. So if I want to fit the data set a regression to the previous scatter plot, so we can create a plot, and now I can use the command apply. So apply, so I recall exactly the name of the regression model fitted. So you can type the apply, and then it creates. I think we have to do it immediately after each other. So create here, and then the regression line, and then the line. What's the problem with this one? Let me see. Let's wait with it. We call entire of them. Then you'll see that here we calculate this. Maybe one thing you can do, I encourage you to calculate the regression before this one and record the regression before this. And once we have the plot, and then immediately it fit, because for the outline first you need to have a plot already, so it creates the scatter plot and then attach the outline to your scatter plot. And that's why you'll see that the blue line, which I determined the color of blue, is the regression line fitted to the data set, and you'll see that blue line is very well describe the relationship between them because the correlation is high, is 0.8, positive 0.8. So the next thing that we want to learn is how to calculate the, I think it's 18 minutes, so I stop here and then, okay, I think I'm thinking that we did it in the last section, so I'll stop the call and continue. So the next thing is that we want to learn how we can use R to do calculation for normal distribution. So let's start. You know that when we learn normal distribution, we have two types of examples. One, the first example is that sometimes we have an observation and we want to find the probability corresponding to that observation, probability of the left side or the right side of that observation. So first we consider that we have the observation and we want to find the probability to the left or to the right of that observation. So let's look at the example. I think this is the example we did in class, but once we solve it, but here we want to do it by R. Assume that the heights of a population are normally distributed with mean 68, mean of the population is 68, and the standard deviation is 2.5. Now we want to find out what is the probability of the randomly selecting someone who is less than 65 inches. So less than 65 inches, it means that we want to calculate the area to the left of 65. Under the curve to the left of 65. So the first step is that as we learn, we have to find the z-score corresponding to 65. So a standard score, so in other words, observation minus mean of the population, which is 68, divided by a standard of the population, 2.5, so it gives us Z1, the z-score corresponding to 65. And we want to see that. What is the z? Z is the negative 1.25. And then this time we don't need, because when we have RStudio, we don't need to have access to the table of the standard normal distribution, because we can calculate directly into those probabilities by R. So we can use the command pnorm. Pnorm, it means that gives me the probability of the area on the left side of this Z1. And pnorm, if you write it, so it means that pnorm, it gives you 0.11 50, or this is exactly the same as if the default of this one is that pnorm when mean is 0, because it's a standard deviation and a standard deviation 1. So because when we don't specify the mean and the standard deviation, the default is that you are looking for the pnorm from the table of the standard normal distribution. That's what if you see, you calculate, you get exactly the same value. But what thing we can do, we can calculate the entire of this process directly by one line, because we know that 65 is the percentile of this normal distribution, this member of the normal family. So I can calculate, I want to find the area to the left of the 65 when directly we determine for R that our population is not a standard normal distribution. This 65 comes from the normal with mean 68, and the standard deviation 2.5. And if you type it, you can do all previous steps in one line, and it gives you exactly the same value we found in the previous calculation. This is the technique we use when we have an observation and we want to find the probability. So this is about the probability on the left side of the 1 percentile. So what about if I want to calculate the area to the right of the 65? Very simply, because P norm gives you the probability of area on the left side of the Z, so you know that the second requirements of the second rule of the third rule of the probability model. So the area to the right is 1 minus the left area. So simply you can calculate 1 minus probability with 1, and it gives you that the area on the right side of the 65. Or you can type it the same as before. Here P norm, copy here, paste. So I want to determine that my observation 65, but it comes from the normal distribution with this parameter, and I'm interested on the left side, the right area of this point. If you calculate, you will see that you get exactly the same value as 0.88. That's the case when we have observation, but we want to find the probability. What about the next scenario is that we have the probability for a given probability we want to find an observation or percentile. So for example, consider this case, what height represents the 19th percentile of the population. In other words, we have the probability 9%, but we want to find the point that the area to the right of that percentile is 90%. So in order to, when you have the probability and you want to find the quantiles or percentiles of the, in the class we talked about the percentile, but in ours, everything's about quantiles. So if you want to find the percentile of the normal distribution, so it's better you need to work with the command qnorm. It means the quantiles of the normal distribution. Remember the previous one was the probability of normal distribution qnorm. This one is the qnorm. And qnorm, you need to provide the probability you want. So I want to find the z such that the area to the left of z is 0.9, and if I run this command, the value is 1.28. Or sometimes you have, because this is the quantiles of the standard normal distribution. So one thing is that you can find it quantiles of the standard normal distribution, that we call it Z2. And then now because by cross multiplying, you have the Z, you have the mean, you have the standard deviation, now you find the observation corresponding to this, because this is the quantiles of the or percentiles of the standard normal distribution. But you're looking for an observation from the original normal distribution. So that's why you multiply by the standard deviation plus the mean, cross multiply, and we get exactly the value of the percentile of your original normal distribution. In other words, 90% of observations in this normal distribution is less than this value. But you can do everything very simply by just writing qnorm, and I'm looking for the 19th percentile of this distribution, but I know that my original normal distribution has a mean 68 and a standard deviation 2.5, and you don't need to first calculate standard normal distribution and then cross multiply by qnorm and determine the mean and the standard deviation of your original population. It gives you exactly the same as the same. The next thing that I forgot, I think, to write it, but you can write, is that I want to generate the data from the normal distribution. How can I generate the data? For example, I know that my We can use by command rnorm, randomly generate data from normal distribution. You see that once we type it, here's a box. It tells you that you need to determine how many observations do you want to have from this normal distribution. I want to have, for example, 500 observations. For example, generate for me 500 observations from normal distribution with mean equals to the same, for example, the same population 68 and the standard deviation the same as before 2.5. So if you run it, so you see that you clearly see that there are generated for you 500 observations from this normal distribution. And if you simply call this one as your data generated, for example, x height generated, h generated. So I call this one data h generated. Now I want to have histogram of the h generated. So if you run it, you'll see that I couldn't find that histogram of the norm, and then here it gives you that histogram of your data set. So this is the end of the Computer Lab 6. Thank you for your attention.